Hello everyone, my name is Simin Chen. Today, I'm pleased to present our latest work, The Dark Side of Dynamic Routine Neural Networks Towards Efficiency Backdoor Injection. This work is cooperated with Hanlin and Milazzo, advised by Dr. Liu and Dr. Yang. Today, deep learning is pervasive on edge computing. Deep neural networks have been applied to automation driving, facial recognition, robotics, and mobile and IoT devices. However, modern deep neural networks usually contain millions of neurons and require billions of floating point operations. When deploying those large deep neural networks on resource-constrained edge devices for decision-making, the computational cost of this application will be a great issue. Considering the mismatch between the huge computing amount of deep neural networks and the constrained computing resources of edge devices, and the observation that not all inputs require the same computational resources, researchers proposed dynamic neural networks. As shown in this figure, dynamic neural networks will allocate different computational resources for different inputs. Based on this observation, we raise this research question: can we inject efficiency backdoors into dynamic neural networks that only affect dynamic neural networks' computational efficiency on triggered inputs, while keeping dynamic neural networks' behavior in terms of accuracy and efficiency unchanged on benign inputs? Recall that there are series of existing work trying to understand the vulnerability of deep neural networks. However, none of them studied the backdoor vulnerability or efficiency backdoor vulnerability of neural networks. We summarize three properties of the efficiency-based backdoor attacks. First, our attack should be unnoticeable to users. Second, the attack should be effective to degrade models' efficiency on triggered inputs. Last, after injecting the backdoor, the model should behave normally on benign inputs. We formulate these three properties as an optimization problem, as shown in this equation. Here, this constraint represents the backdoor trigger should be minor and not unnoticeable. And our optimization goal is to maximize the computational cost of the victim model. And here, the constraint here represents we push the model to behave normally on benign inputs. This figure shows our design overview. Our intuition is that the uniform distribution is the optimal distribution that will result in the dynamic neural network consuming the most computational resources among all distributions. With such intuition, we design a novel objective function and make the efficiency backdoor injection problem, transfer the efficiency backdoor injection problem into a supervised problem. I will not go into detail of our approach. For readers who are interested in our approach, please refer to our paper. And this algorithm shows how we train our optimal backdoor trigger and how to inject the backdoor trigger into the victim model. We then evaluate our approach on two datasets, CIFAR10 and Tiny ImageNet. We choose for each dataset. We choose three model backbone: VGG19, MobileNet, and ResNet. We use two training algorithms to train the dynamic neural networks: the intermediate classifier, separate training, and shallow deep. We mainly answer two research questions. First is, how effectiveness of proposed approach? The second is, can our approach inject a backdoor and produce a stiffness victim model? For the first research question, we define two metrics. The first is the computational complexity on triggered inputs, and the second is the EEC scores. For the stiffness evaluation, we use the SSPD distance and the Haas drop distance as our evaluation metrics. Table 1 and Table 2 shows our effectiveness evaluation results. For more evaluation result details, please refer to our paper. And the Table 3 shows the stiffness evaluation results. We then visualize the accuracy and the efficiency score of backdoored model on clean and triggered inputs, and the red and clean model on clean inputs. As shown in this figure, after injecting the backdoor, the model will behave abnormally on triggered data, as shown in the red curve, but will behave very closely to the clean model on clean data, the red and yellow curve in the figure. Okay, we conclude this work. We first characterize the efficiency backdoor vulnerability in dynamic neural network models. We propose an attack algorithm to inject efficiency backdoors, and our evaluation results suggest the effectiveness of our proposed methods. Thank you.